you're just pitching me before we hit record that we are, living in the final days of the human bottleneck, and that I need to prepare for our new algorithmic overlords.
Because we are. I mean, look at the metrics. The latest large language models are processing, trillions of parameters a second.
Right.
They're writing code, generating entire virtual environments, fundamentally rewriting how we interact with information. Software is literally eating the world. We're hitting a point of just like pure, untethered computational magic.
Well, I checked the math on your computational magic, and it's a mess.
Oh, come on.
No, seriously. Algorithms are completely useless without a physical piece of rock to run on. Hyping up the software revolution while entirely ignoring the hardware is it's like praising the absolute genius of a sheet music composer while completely ignoring the fact that someone actually has to chop down a tree, string the wire, and build the piano.
You're pulling me back to the dirt. You always do this. I'm trying to look at the infinite possibilities of the cloud, and you're dragging me back to physical constraints.
The constraints are the only thing keeping reality intact. And that brings us to the mission for today's deep dive. We are unpacking Chris Miller's fascinating book, Chip War.
Such a good book.
It really is. The goal here is to understand how the world's most critical technology, the semiconductor, dictates global economics, military power, and why the entire modern world is completely dependent on a few, honestly, wildly precarious choke points.
Yeah, fragile is an understatement.
Right, because whether you are listening to us right now on a smartphone, driving a car, or standing in front of a smart fridge trying to decide what to eat, your entire daily life relies on a physical object that is currently the epicenter of a geopolitical Cold War.
It is the foundation of the modern era, period.
But our baseline understanding of this technology is terrible. We talk about the cloud as if our data is literally floating in water vapor above us. It's not.
Not at all.
It's sitting in massive, temperature-controlled warehouses on microscopic grids of billions of transistors. Believing it just exists in the ether is like thinking a car runs on gasoline fumes and good vibes without understanding the engine. So before we get carried away with the boundless future of AI, I need you to establish what a chip actually is and the sheer chaotic human effort it took to build one.
Okay, fair enough. To really grasp the leap we've made, you have to look at what computing used to be. In the 1940s, early computing was a massive industrial endeavor.
Giant machines.
Exactly. The U.S. Army built the ENIAC computer to calculate artillery trajectories for World War II. This thing used 18,000 vacuum tubes, which were essentially fist-sized glass light bulbs. It weighed 30 tons and took up an entire room.
And it was famously a nightmare to maintain, right?
Yeah, a total logistical disaster. Because these glass tubes glowed with immense heat, they attracted literal moths in the facility.
Literal bugs in the system.
Yes. The insects would fly in, fry themselves on the tubes, and short-circuit the entire artillery calculation. The engineers had to walk inside the computer to do literal debugging, like pulling dead moths out of the circuitry with tweezers.
See, if your logic gate is a fragile glass light bulb that burns out every few hours or gets taken down by a stray insect, you can't exactly scale that up.
No, not at all.
You certainly aren't fitting it into a guided missile, let alone a pocket-sized phone.
Right, so you need a fundamentally different kind of switch. Right. Enter the transistor, invented at Bell Labs by Walter Brattain and John Bardeen. It performed the exact same job as a vacuum tube, controlling the flow of electricity, turning it on and off to create the binary ones and zeros of digital logic.
But without the glass and the heat.
Exactly. Instead of a fragile glowing filament in a vacuum, it used solid pieces of semiconductor material. First germanium, then silicon. No heat glow, no glass, no moths. It was a solid state revolution.
Okay, so the physics were revolutionary, but the human element was an absolute mess. The drama really starts with William Shockley, right? He won the Nobel Prize for his theoretical work on semiconductors. A brilliant physicist, but by all historical accounts, an impressively toxic manager.
Toxic is an understatement. He founded Shockley Semiconductor in California to commercialize these new transistors, but he was incredibly paranoid. Like he was definitely gatekeeping the best parts of the physics from his own team.
Wow.
Yeah, he would pit researchers against each other, secretly record phone calls, and completely alienated the brilliant young minds he had recruited.
It's somewhat comforting to know that petty startup drama hasn't evolved a single bit since the 1950s.
It really hasn't.
His management was so suffocating that 8 of his top engineers, who he later dramatically dubbed the traitorous 8, walked out on him. They abandoned his company to found Fairchild Semiconductor. That single walkout is essentially the Big Bang of Silicon Valley.
It really is. And two of those traders were Gordon Moore and Bob Noyce. And Noyce, running parallel with an engineer named Jack Kilby over at Texas Instruments, independently figured out the next massive conceptual leap.
The integrated circuit.
Yes. Up until then, if you wanted a complex computer, you had to wire a bunch of separate transistors together by hand. It was messy, prone to human error, and took up way too much space. They realized, what if we stopped wiring individual components together? What if we carved multiple transistors into a single continuous block of silicon?
And boom, they birthed the microchip. But, and here's my pushback, understanding the theory of a microchip and actually making one are two very different things.
Fair.
Inventing a chip in a lab is just a highly expensive science fair project unless you can mass produce it. How do you transition from soldering wires by hand to printing millions of microscopic connections on a tiny sliver of rock? I mean, it sounds like trying to paint the Mona Lisa using a commercial bulldozer.
The bulldozer.
Yeah.
Okay, that gap between theory and manufacturing is where the true unsung heroes of this story live. The solution to your bulldozer problem came from an engineer named Jay Lathrop.
Okay, what did he do?
So he was working for the military on proximity fuses for mortar shells, desperately trying to shrink the electronics. Lathrop had this completely chaotic but brilliant realization involving a microscope.
A microscope.
Yeah. Normally you look through a microscope to take something microscopic and blow it up to a visible size. Lathrop just asked, hey, what if I use it backwards?
The brute force simplicity of that is incredible.
I know, and it changed human history. By shining light through an inverted microscope, he could take a large, easily drawn pattern and shrink it down to a microscopic scale.
Wait, how does light carve a pattern, though?
He coated a piece of semiconductor material with photoresist chemical stuff originally developed by Kodak that reacts to light. When he shined the light through his upside-down microscope, it projected a microscopic, perfectly scaled pattern onto the chemical coating.
Oh, wow.
Yeah, the areas hit by light hardened, allowing them to wash away the rest and etch tiny, precise channels into the silicon. He invented photolithography. He figured out how to print transistors using light.
Which fundamentally changes the economics of the entire industry. Because once you can print chips with light instead of assembling them by hand, the objective completely shifts to scaling.
Right, exactly. Scaling that.
Packing as many transistors onto a single piece of silicon as physically possible. Initially, this push wasn't driven by consumer demand. It was entirely bankrolled by the Cold War military-industrial complex.
The Pentagon was the ultimate angel investor here. The Air Force needed ultra-lightweight, reliable chips to shrink the guidance computers for the Minuteman II nuclear missiles. NASA needed them for the Apollo program.
Because weight is everything in space.
Exactly. They had to take a calculator that used to fill a room and shrink it down to a 70-pound box that could actually survive a trip to the moon.
But Gordon Moore, one of our traitorous 8, saw a horizon beyond just government contracts. In 1965, he published an observation that the computing power on a chip would double roughly every year or two as engineers continuously refined this printing process to make transistors smaller.
Yes.
And this became immortalized as Moore's Law.
The defining metric of the digital age. It's honestly the closest thing we have to a magic spell in technology. It dictated that computing would inevitably, reliably get exponentially cheaper and faster, unlocking the personal computer, the internet, and everything we have today. It's just magic physics.
Yes, and let's ground that magic spell for a second. Moore's Law wasn't a law of physics. It wasn't gravity. It was raw, relentless capitalism.
You're killing my vibe with these facts.
I know. But Bob Noyce intentionally slashed the prices of Fairchild's chips, frequently selling them at a massive loss, just to force a civilian market into existence. Moore's Law only held true because manufacturing bosses, like Charlie Spork, were barking at employees to increase factory yields and cut costs.
It was an intense culture.
The driving force was financial incentive. Chris Miller highlights an exit interview from a Fairchild employee that cuts through all the romanticism. When asked why they were leaving for a competitor, the engineer just wrote, all in caps, I want to get rich.
Okay, yeah, that intense financial motivation definitely willed the innovation into existence. And it's exactly what the Soviet Union completely failed to understand.
Right, because they tried to copy it.
They did. The Soviets recognized chips were important, and they tried to keep up. Alexander Shokin, a top Soviet bureaucrat, literally handed his engineers a smuggled Texas Instruments chip and ordered them to, and I quote, copy it one for one.
Just duplicate it.
Yeah, they built Zelenograd, a massive secret city outside Moscow, designed to be their Silicon Valley. They deployed KGB spies to steal American chip designs and set up shell companies to smuggle in American machinery.
But, okay, if you steal the blueprints to a house, you can build the house. The Soviets successfully stole the exact blueprints. Why couldn't they manufacture the chips?
Because a chip isn't just a schematic. That's the trap Shokin fell into. A chip is the physical manifestation of an ultra-efficient, highly specialized global ecosystem.
Oh.
To manufacture that stolen design, the Soviets needed ultra-pure silicon. They needed specific photoresist chemicals that were constantly being updated. They needed flawlessly manufactured microscopic masks. The United States had organically built an international supply chain.
Right, pulling from everywhere.
Exactly. They were sourcing chemicals from Japan, lithography optics from Europe, and setting up testing and assembly in Southeast Asia. You can smuggle a blueprint in a briefcase, but you cannot smuggle a global ecosystem. By the time the KGB got a design back to Moscow and the engineers figured out how to replicate it, Silicon Valley had already iterated 2 generations ahead.
So free market capitalism and global trade essentially gave the U.S. the edge in the Cold War. But that exact same globalized supply chain eventually fostered a brand new, terrifying rival for Silicon Valley, which was Japan.
Oh, the 1980s trade panic. Japan, led by consumer electronics visionaries like Akio Morita at Sony, took the semiconductor manufacturing process and just perfected it.
They made it incredibly efficient.
Yes, they brought extreme precision and quality control to the memory chip market, the DRAM chips. By the mid-80s, Japanese firms were completely dominating U.S. companies. Silicon Valley was in a full-blown existential crisis. Jerry Sanders, the legendary CEO of AMD, famously declared that semiconductors were the crude oil of the 1980s.
The U.S. response to Japan's dominance is fascinating because it relied on 2 deeply American concepts: cowboy capitalism and military supremacy.
A wild combination.
Very. On the capitalism front, you had characters like Jackson Plott. He was an 8th-grade dropout who became a literal billionaire potato farmer from Idaho. He was the potato chip king.
I still can't believe this guy.
It's true. And out of sheer competitive spite, he threw his potato fortune into funding Micron, a struggling U.S. memory chip startup, giving them the cash to survive the Japanese price war.
The fact that our digital infrastructure was saved by a potato baron is just incredible. And alongside that, the Pentagon stepped in with the offset strategy.
What was that exactly?
They looked at the Soviet Union's massive tank armies in Europe and realized the U.S. could never match them, vehicle for vehicle. So they decided to put advanced microchips into everything. They funded the development of precision-guided munitions, stealth aircraft, and advanced sensor networks.
And the devastating reality of that strategy was broadcast live to the world during the 1991 Gulf War.
It was a total paradigm shift in warfare. The world watched footage of laser-guided bombs flying down ventilation shafts and dismantling an entrenched army with terrifying precision. It wasn't about the size of the bomb anymore. It was about the computing power guiding it.
Right.
The entire globe realized simultaneously that microchips were the new currency of military dominance.
But while the U.S. was hyper-focused on beating back Japan and integrating chips into weapons, a completely different model was quietly being born in Taiwan and would eventually upend the entire industry.
Oh, Morris Chang.
Exactly. The Taiwanese government recruited Morris Chang, a veteran executive from Texas Instruments, to build their domestic tech sector. Chang created TSMC, the Taiwan semiconductor manufacturing company, and he introduced the foundry model.
Is the most brilliant pivot in business history.
Sure.
Chang looked at the landscape and said, TSMC will never, ever design its own chips. We will not compete with our customers. We will only manufacture chips designed by other people.
A pure manufacturer.
Yeah, he built the ultimate kitchen and told the world's best chefs, I won't write recipes, but send me your recipes and I will cook them better, faster, and cheaper than you ever could.
Wait, a chef who doesn't write recipes but just cooks them really well.
Okay, fine. The metaphor is breaking down, but you get what I mean.
Yeah.
Suddenly, any brilliant engineer in a garage with a software design could just email their schematics to TSMC and have physical chips shipped back to them.
So he basically became the Gutenberg of the digital era, but instead of just inventing the printing press, he monopolized it, which is a fascinating shift in tech culture, because Silicon Valley executives used to strut around boasting that, quote, real men have fabs.
Yeah. Fabrication plants?
Right. They believed controlling the physical factory was essential to the business. Why was giving up manufacturing the smartest thing U.S. companies ever did, and simultaneously the most dangerous?
Well, it was smart because manufacturing was getting exponentially more expensive. To keep Moore's Law alive, To keep shrinking these transistors, building a single new factory started costing billions of dollars. Companies like Apple, Qualcomm, and Nvidia realized they could outsource the financial bloodbath of manufacturing to Taiwan.
You just offload the risk.
Exactly. They could focus entirely on the highly profitable design architecture and let Morris Chang spend the billions on the physical fabrication plants. It was wildly efficient for U.S. balance sheets.
But there's a catch.
A massive catch. Chang's foundry model slowly concentrated an unfathomable amount of power. He created what he called the Grand Alliance. By making everyone rely on him, TSMC achieved such massive scale that they became the only company on Earth that could economically justify the mind-boggling research and development costs of next-generation manufacturing.
Which brings us to the terrifying reality of today. The entire global economy is balancing on a few incredibly fragile choke points.
Oh, yeah.
Let's examine the most absurd choke point in this entire supply chain. It's not in Taiwan and it's not in Silicon Valley. It's a company in the Netherlands called ASML.
ASML literally breaks my brain. They hold a 100% global monopoly on a technology called extreme ultraviolet lithography, or EUV.
Okay, break that down for me.
Remember J. Laserup's upside-down microscope shining light to print patterns?
Yeah.
Today, the transistors are so unfathomably small, measured in nanometers, literally smaller than a coronavirus, that normal light is physically too fat to draw the lines.
The wavelength of visible light is just too wide to carve the transistor.
Exactly. So ASML had to create a machine that generates extreme ultraviolet light. And the way they do it sounds like science fiction. Inside this machine, they drop a microscopic bead of molten tin.
Molten tin.
Yes. And while it's falling at 200 miles per hour, they shoot it with a high-powered laser. Not once, but twice.
We kidding.
I'm not. The first laser flattens the tin into a pancake, and the second laser vaporizes it into plasma. That exploding plasma emits a flash of extreme ultraviolet light. That light is then collected and bounced off the flattest mirrors ever manufactured by humans to carve a pattern onto silicon. And they do this 50,000 times a second.
That is absurd.
It is arguably the most complex machine in human history. It took decades of research and billions of dollars to perfect. And ASML is the only company on the planet capable of building one.
And those ASML machines are shipped to Taiwan, where TSMC uses them to actually print the chips. Just to put the scale of this production into perspective for you, the Apple chip inside an iPhone 12 has roughly 11.8 billion transistors on it. In just a matter of months, one single facility in Taiwan TSMC's Fab 18 produced 1 quintillion transistors for Apple alone. That's a 1 followed by 18 zeros.
The scale is paralyzing. I mean, last year, the semiconductor industry manufactured more transistors than the combined quantity of all other goods produced by all other industries in all of human history. The typhoon of steel that defined industrial power in World War II has been completely replaced by a typhoon of silicon.
Okay, you're getting hyped, but you are killing my vibe with the reality of this. Because that quintillion transistor factory sits on an island prone to severe earthquakes right on a major fault line.
True.
But tectonic plates are honestly the least of the tech industry's worries right now. The real threat is the clash of superpowers.
Absolutely. China looked at this exact supply chain and realized they have a massive existential vulnerability. They spend more money importing microchips every year than they spend importing oil. Yeah, their entire modern infrastructure, from smartphones and telecom giants like Huawei to their military AI systems, relies fundamentally on foreign silicon, the vast majority of which is manufactured in Taiwan using American and European tools.
And President Xi Jinping recognized this bottleneck. He launched the Made in China 2025 initiative to achieve domestic chip independence, funneling billions into their own manufacturing sector. Because they know that if their access to foreign chips is cut off, their economy suffocates.
Yep.
And Washington realized that too, which is why the United States initiated the chip choke.
It's an incredibly aggressive geopolitical maneuver. For decades, the U.S. strategy was just to run faster, innovate quicker, stay ahead of the competition. But they realized running faster wasn't working anymore because the U.S. share of global manufacturing was rapidly shrinking.
Right, it wasn't enough anymore.
So they switched tactics. They decided to kneecap the competition by weaponizing the supply chain.
And the mechanism they used is fascinating. It's called the Foreign Direct Product Rule. It essentially dictates that if a product is made using American technology, software, or equipment anywhere in the process, the U.S. government can dictate who it gets sold to.
It's hugely leverageable.
Massively. By barring companies like Huawei from using any tech that relies on U.S. patents, which, thanks to our ecosystem, is almost all of it, They legally cut off China's access to the world's most advanced chips. And as Chris Miller points out impartially in the book, this wasn't a partisan whim. This strategy was initiated by the Trump administration and aggressively expanded by the Biden administration.
We built a beautifully interconnected global economy, and now we're practically holding it hostage because all of this maneuvering centers on Taiwan. I mean, here's the big truth. Taiwan produces 37% of the world's new computing power each year, and effectively 100% of the most advanced cutting-edge processors.
Which means Washington spent decades preaching that free trade and global supply chains made the world safer. The whole theory that intertwined economies don't go to war. But now, they are leveraging that exact interdependence as a weapon. Aren't we just putting all our global economic eggs into a basket that sits squarely in a geopolitical war zone?
We are. If there is a blockade or a military conflict in the Taiwan Strait, the fallout wouldn't just mean a delay in the next smartphone release.
Right, it's so much bigger than that.
Global car manufacturing would grind to a halt, telecom networks would stall, the data centers powering the cloud, AI, and the financial sector would freeze. We are talking about an economic catastrophe that would absolutely dwarf the 2008 financial crisis.
Okay, let's synthesize all of this. Mission complete on our deep dive today. What we've uncovered is that tech isn't just software. It's not magical algorithms floating in the ether.
Right.
It is incredibly complex physical hardware. It is a fragile, sprawling global supply chain born out of a bizarre cocktail of Cold War paranoia, military strategy, and relentless profit-driven capitalism.
The physical rock of silicon dictates everything. The software is really just a guest in the hardware's house.
Exactly. So, for you listening, I have a deadpan homework assignment for you.
Oh, yeah.
Yes. I want you to look around your house, find the oldest electronic device you own, and try to trace every single country involved in manufacturing the chip inside it. Spoiler alert, you are going to need a massive world map and a lot of red string to connect the dots.
That sounds like so much work. You are totally killing the magic of the future for me. See, you can focus on the fragile geopolitics of that supply chain all you want, but you are missing the sheer human triumph here. We figured out how to shoot liquid metal with lasers to trick rocks into thinking. That complex web of countries isn't just a vulnerability. It is a masterpiece of global cooperation.
It is a masterpiece, but it's a masterpiece with physical limits. And I'll leave you with one final provocative thought to chew on. For 60 years, Moore's law guaranteed that computing power would get cheaper and exponentially more powerful. But physics is undefeated. We are already carving transistors the size of viruses. As we reach the absolute atomic scale and Moore's law inevitably grinds to a halt, who wins the global power struggle when we can no longer rely on simply making things smaller? Because the next time someone tells you algorithms are running the world, remember the world is actually running on a very small rock, and we are rapidly running out of room on it.